Let's look at this reaction to make methanol from carbon monoxide and hydrogen. 1 mole of carbon monoxide makes 1 mole of ethanol. 2 moles of hydrogen are needed to make 1 mole of methanol. So it's a reversible reaction, so it can go in forward and backward directions. At the start of the reaction, I've got 0.73 moles of carbon monoxide. I've got 1.25 moles of hydrogen, and I won't have any methanol because none is made yet. The reaction hasn't started. At equilibrium, so that's a point where the forward and backward reactions are going at the same speed or the same rate, and the concentrations of reactants and the concentrations of products are no longer changing at equilibrium, sometimes called dynamic equilibrium. At that point, I've made 0.43 moles of methanol. When I make 0.43 moles of methanol, because 1 mole of carbon dioxide makes 1 mole of methanol, if I make 0.43 moles of methanol, I must need 0.43 moles of carbon monoxide to make that 0.43 moles of methanol. So the amount of carbon monoxide that I've now got is what I had initially, 0.73, take away 0.43. 0.30. If you look here, everything here is to two significant figures, so I've put these to two significant figures as well. 0.30. Now then, the problem is when I make 0.43 moles of methanol, I need, for every 1 mole of methanol, I need 2 moles of hydrogen. So to make 0.43 moles of methanol, I must use up 0.86 moles of hydrogen. I started off with 1.25, take away 0.86 equals 0.39, again to two significant figures. Write an expression for the Kc, so that's the concentration of methanol divided by the concentration of carbon monoxide divided by the concentration of hydrogen. Concentration of hydrogen needs raising to the power 2, it needs squaring for the equilibrium constant because there's a 2 in front of the hydrogen, so that's your equilibrium constant expression. In another experiment, the equilibrium mixture contained, so I've got the moles of each of the three and I've got the volume. Why would I be given the moles of each of the three, the carbon monoxide, the hydrogen, the methanol and the volume? The only reason I'd be given moles and volume is to work out concentration. So the concentration, well, concentration is moles, and I've got the moles, but it's divided by volume in decimeter cubed. Centimeter cubed into decimeter cubed, a small unit, centimeter cubed, into decimeter cubed, I'm going to divide by 1,000. So 9.4 times 10 to the power of 3 centimeter cubed divided by 1,000 is 9.4 decimeter cubed. And then if I divide each of these molar amounts, moles, by 9.4, I'll get the concentration of each of them. So the concentration of methanol 0.029, concentration of carbon monoxide 0.0481, concentration of hydrogen 0.1128. So I'm dividing by 9.4 the volume in decimeter cubed. They're all in the same flask, so the volume is the same, 9.4. I put these numbers into Kc and it comes out as a number 4.75 times 10 to the power of 3. What are the units then? Well, let's have a look at the units here. So units of concentration are moles divided by decimeter cubed. Moles divided by decimeter cubed. I've got one concentration on the top and I've got 1, 2, 3 concentrations, because this concentration is squared, 3 concentrations on the bottom. So if I put those into my units, moles divided by decimeter cubed, moles divided by volume in decimeter cubed, 1 on the top, 1, 2, 3 on the bottom. 2 of those, top and bottom, 1 at the top, 1 at the bottom, cancel to leave just nothing on the top, or rather a 1 on the top, divided by mole divided by decimeter cube, mole divided by decimeter cube. These two are still on the bottom. What's another way of writing this? Well, mole divided by decimeter cubed, another way of writing that is mole dm to the minus 3. The minus means you've divided by the decimeter cubed. I've got another one here, mole dm to the minus 3. How do I simplify that? Well, I've got a mole and a mole, which is a mole squared, and I've got a dm minus 3, dm minus 3. I add these two numbers together to get a dm minus 6. If it's on the bottom and I want it to be on the top, I change the 2 into a minus 2 and I change the minus 6 into a plus 6. So I reverse the signs, positive to become negative and negative to become positive if I want this on the top rather than the bottom. The total pressure in the flask was 482.9 kilopascals. I've been given a gas constant and I want to work out temperature. The only reason I'd be given the gas constant if I wanted to use this equation. It's the only equation I know with a gas constant in it. PV equals nRT. So PV equals nRT. Pressure. Pressure here is in kilopascals. I want it in pascals. To turn a large unit into a smaller unit, I divide by multiply by 1,000. So 482.9 kilopascals into a smaller unit of pascals and multiply by 1,000. So the pressure is 482,900 once I've multiplied it by 1,000 to get into pascals. So pressure's in pascals. One of my bigger problems is now that I've got to get volume. So what's the volume? Well, the volume of the flask, because the flask hasn't changed, is 9.4 decimeter cubed. In this equation here, my volume needs to be in meters cubed. So to get decimeter cubed 9.4 into meters cubed, decimeter cubed into a larger unit value of meter cubed, I've got to divide by 1,000. So it's 9.4 divided by 1,000. So that becomes 0.0094 meters cubed. So now I've got the pressure, I've got the volume. N is the number of moles. Well, the number of moles in the flask is the number of moles of all of the gases added together. So the number of moles in the gases in the flask is 0.452, 0.106, 0.273. That's the number of moles of gas that I have in the flask, and that equals 0.831. So I've now got P, I've got V, I've got N, I've got R, which is 8.31, and if I put all of that in, I end up with this equation here. T I don't know, that's what I'm trying to find, so I'll multiply these numbers out first. It's probably easier to do that first on your calculator, and then temperature is 4539.26 divided by 6.906, which is 657.3. Now temperature is in Kelvin, and it asks for it in degrees C. To get the final mark, then you need to convert Kelvin to degrees C. You subtract 273, you take 273 away from this value. So if you turn in degrees C into Kelvin, you add 273, Kelvin into degrees C, you subtract 273, and so the answer comes out as 384.3. If you look at all of the numbers here, well, 8.31 certainly is to 3 significant figures, so is 9.40 for the decimeter cube. So my lowest accuracy value is to 3 significant figures. That's to 4, so it's best if I turn it to 384 and get it to 3 significant figures.